Hello, my name is Eamon. I'm a member of Epsilon Pi Epsilon International Honor Society for the Computing and Information Disciplines, and I study computer science and software engineering at the University of Washington. This is part 2 of the using the GPIO pins to run game controllers on the Raspberry Pi tutorial. I will be discussing the wiring of the controller, and that will be followed by a demo. And the code should be available in some of the links I provide below, and you can feel free to take a look at that. It's not meant to be plug and play, it's meant to be difficult to use. I've only implemented up, down, left, right for the controller, so if you want to add additional functionality, you can feel free to do that, but it's not intended to be complete software. It's meant to be something for someone to take and figure out and extend and so on. So, how about it? This first slide here is the wiring of the 9-pin D-sub that we're going to be connecting, 9-pin D-sub connector that we're going to be connecting to the Atari 2600 controller, and this is how it's hooked up via a breadboard. If you'll notice in yellow, we have the 3.3 volt pin coming from the Raspberry Pi, and like I said, some pinouts will tell you need 5 volts, but you don't need 5 volts for the Atari, and the only Atari controllers that had a 5 volt in were the controllers with additional functionality from a potentiator, like the Pong controllers and some other specialty controllers. And below that, you see in yellow are just connectors. So the 3.3 volt pin causes that whole channel on the right that's lit up in red to be active, and the connectors hook up a lateral channel and makes that active there. In red, we see the black ground that goes to the 9-pin D-sub connector. As I discussed earlier, the Atari 2600 is an active low short to ground controller. On the opposite side of the breadboard, we have the Atari 2600 control pins. Those go directly to the 9-pin D-sub that we're going to plug the Atari 2600 controller in. Bridging that breadboard are the 10 kilo ohm resistors, which act as the connector between the 3.3 volt current and the control pins. And in series with that are, in green there, you can see we have the female to male pins that connect to the Raspberry Pi GPIO pins. And how this works is the Atari 2600 is an active low short to ground controller. So there's constantly current running through the via the 3.3 volt pin, through the connectors, through the resistor, through that lateral channel there to the GPIO pins. So they're constantly reading a positive current. And when you hit a button or you touch a direction on the Atari 2600, it shorts to that ground pin that's noted there in red. And what that does is draws a large amount of current, and that causes the current that gets through to the RPI's GPIO pin, which is in series with the Atari 2600 pin, to drop below its threshold voltage. So it becomes low, zero, logically false. So it's an active low controller, and we respond to that state. And I discussed how to respond to those states in the first part of this tutorial, and if you examine the code that I've provided, you can hopefully get a good understanding of how that works. And here we're going to be looking at the 9-pin D-sub connector. These are cheap. You can get them for, I got this for a couple of dollars at a local electronics store. It fits the Atari 2600, the Sega Master System, Sega Genesis, some other popular old school joysticks for the computer. And on the back of the 9-pin D-sub here is is they're kind of like hollow tubes, and you can fit your jumper cables right into the back of them. So these are male jumper wires that I've soldered into these little tunnels here on the back of the 9-pin D-sub connector. Obviously, they get familiar with how to safely solder and follow all the precautions there before you try and use solder. And I would recommend the protective eyewear, because it can get a little explosive sometimes when you're soldering. It can kind of pop off, and you might accidentally injure yourself. So it's definitely better safe than sorry. So these pins go directly to the excuse me, the breadboard, and those are the pins that I had labeled earlier as 2 9-pin D-sub, and those will directly interface with the Atari via the connector. And I'll show you this whole system view here. You see we have the Atari 2600 on the left. It's directly connected into the 9-pin D-sub. Those wires run to the breadboard. Those wires from the breadboard run to the Raspberry Pi. And when low signal is detected, the Raspberry Pi can respond with the U input. I haven't been able to get the driver to work with all programs. Oddly enough, Stella doesn't behave correctly with the program. It operates fine in the menu, but once you start the emulator, it doesn't work. I've seen some people discuss similar difficulties with Stella, and some programs don't recognize the virtual device that you generate, but it works for, I'd say, the majority of programs. And you can also replace the keyboard events that are in my program that I'm using with relative access events, which are the mouse events. And some emulators run off of relative access events, so it's possible you'd have better luck with using relative access events. And links to the man pages and things of that nature are found in the code, and it's fairly well commented, so you should be able to figure it out. The only difficult part, if you're not familiar with pointers or bitwise operations, is making yourself familiar with those and understanding how hexadecimal values are converted to binary values, and how the binary values and logical ands and other bitwise operations are affecting registers. And there are links to the information relating to GPIO registers in the first part of this tutorial. Now I'm going to switch over to the RPi, and we're going to do a short demonstration of the software, and that'll conclude the tutorial. Okay, here we are on the Raspberry Pi desktop here. I've already loaded up the program to demonstrate. Star Pusher works pretty well with it. Looks good, so I figured I would demonstrate the driver here. And this is the getPins class. This is the class that returns values from the GPIO pin level register. We have GPIO 3, which is just happened to be the third incarnation of the main program that uses these classes that I use here. And setPins is the class that sets particular GPIO pins as input, output, or if you happen to want to modify it, you could also reuse this and set things as universal asynchronous receiver transmitters, pulse wave, etc. And UI device SNES was originally created for the Super Nintendo Entertainment System. I just didn't happen to rename it again later. This is what makes the virtual device that creates the keyboard events. Again, you could easily modify this object to create, or excuse me, this class to create relative access events, and it's pretty user friendly if you want to add more keystrokes, if you want the device to be allowed to make X's, P's, asterisks, or whatever you happen to want to add. It's pretty easy to do that. I haven't implemented all of the functionality, just it's kind of a challenge left to the user at home. I implemented up, down, left, and right. That's all I have programmed in right now, and the button also isn't programmed in here. You would have to do that yourself. And setPins is also pretty easy to modify. It as a default constructor that simply uses pins 22, 23, 24, and 25 as up, left, right, down. there's another constructor that takes an argument, so you can alter the pin mask and the register offset. That's explained in the file if you want to do that. And get pins you can also modify and get different values if you happen to want to get different values. If you want to get the pins from GPIO pin level register 2, you can do that. Alright, so I'm going to go ahead and run the program. I've already compiled it, so don't need to do that. I do need to run it with sudo still, and I've named my object GPIO test. Okay, so it is now running. I could have run it as a background process, but I just decided not to. I'll hit left. There you see the left symbol. Hit right. Hit down. Hit up on the joystick. Up, 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 etc. And when I switch focus, so the focus is no longer in that window, you'll still see the stub. Still see the stub there, but the up is actually happening on the desktop right now, and the down. The stub is just something I put in there for determining if everything is working correctly and for demonstration purposes as well. I've added a signal handler, so if you want to hit Control C, excuse me, oops, Control C, we'll exit the program, deallocate the file descriptor, and this message is just there's a delay that nano sleeps at the end of the loop to bounce the button input, and if you hit Control C, it fails because it's being interrupted, but there's nothing wrong there. And that's the P error message saying interrupted system call. Here we are destroying the UI device. The file descriptor is free. And if you run that as a background process, the destructor also takes care of this stuff. But if you're running this as a foreground process and you happen to just want to be able to hit Control C, you can do that. So I'll go ahead and run it again and leave it running this time. Click on Star Pusher here and give it a minute to become the active window. Make sure I have focus on the window. Press the key to start. I'll go ahead and press up. Should start here. There we go. Okay. Now let's solve this first puzzle. It's pretty easy. Up, down, left, and right. Puzzle solved. Hit a key to go to the next level. Hit down. Okay, there I am on the next level. And, I don't think I'll solve this puzzle because it's hard and I don't want to embarrass myself by messing it up. But as you can see, it works fine. I'm moving around here, and you can see what's happening there. The window on the right, right, down. And if you happen to want to adjust the sensitivity, you can adjust the delay at the end of the loop where I nano sleep and get it to be more sensitive, less sensitive. This is the level of sensitivity that I thought was best after doing some experimentation. And like I said, the files are there for you to mess around with if you happen to want to do that, and it's not meant to be plug and play because the whole point of the RPI was to be an educational tool, so I didn't want to just put files out there that people could just compile and use. Because I mean, like my professors at the University of Washington. Anyway, have fun with it. Hopefully it's not too frustrating. It's meant to be pretty challenging. Some of the programming that's used in there is pretty advanced stuff, so don't feel bad if you don't get it right away. And good luck with that, and thanks for listening to my tutorials, and that is the end of the tutorials.